Now, generally, neural network embeddings have three primary purposes. Number one, finding nearest neighbors in the embedding space. These can be used to make recommendations based on user interest or cluster categories. Number two, as an input to a machine learning model for a supervised task. Number three, as you'll see here, for a visualization of concepts and relations between those categories. Let's take a look at an example using the popular handwritten digits dataset, MNIST. All right, take a look. Here I visualized in TensorBoard all 10,000 points of data, where each colored cluster corresponds to a handwritten digit from 0 to 9, like if you're writing an envelope to somebody. You can start to look for insights and even misclassifications by just exploring the dataset in 3D space with TensorBoard. If you take a look at the clusters while they spin, you'll see I click on a gray cluster, which are the handwritten 5s. It would seem in this dataset that people write 5s in many different ways, hence the visual distance between the gray squares, not as clumped, compared to something like a 1 or an 8. If you take a sparse vector encoding and pass it through an embedding column, and then use that embedding column as the input to your DNN, and then train that deep neural network, then those trained embeddings will have this similarity property. As long as, of course, you have enough data for your training to achieve good accuracy. Okay, let's take another example. Let's talk about embeddings in the context of movie recommendations. Let's say we want to recommend movies to customers. Now, it could be music or something like that, but let's just use movies because I love movies. Let's say that our business had 1 million users and 500,000 movies. Remember that number. It's quite small, by the way. YouTube and other Google properties have 1 billion users. For every user, our task is to recommend 5 to 10 movies. And we want to pick movies that they'll watch and rate highly. We need to do this for 1 million users, and each user is going to select from those 500,000 movies. So, what's our input data set? If we represent it as a matrix, it's 1 million rows, 1 million users, and 500,000 columns. The numbers in the diagram denote the movies and the customers have watched and rated. What we need to do is figure out the rest of the matrix. To solve this problem, some method is needed to determine which movies are similar to each other. One approach is to organize movies by similarity using some attributes of the movies. For example, we might look at the average age of the audience and put the movies on the line. So cartoons and animated movies show up on the left-hand side, and the darker adult-oriented movies show up on the right. Then we can say that if you like The Incredibles, perhaps you're younger or you have a young child, so we're going to go ahead and recommend Shrek to you. But movies like Blue or Memento are art house movies, whereas Star Wars and The Dark Knight Rises are blockbusters. If somebody watched and liked Blue, then they are likely to watch Memento than, say, a Batman movie. Similarly, someone who watched and loved the Star Wars movies are more likely to watch The Dark Knight Rises than generally an art house genre movie. So, how do you solve this complex problem? Well, what if we added a second dimension? Perhaps the second dimension is the total number of tickets sold for that movie and when it was released in theaters. Now we see that Star Wars and The Dark Knight Rises are close to each other. Blue and Memento are close to each other as well. Same with Shrek and The Incredibles. Harry Potter is in between the cartoons and Star Wars in that both kids watch it, some adults watch it, and it's also a blockbuster. Notice how adding the second dimension has helped bring movies that are good recommendations closer together in our space, and it conforms much better to our intuition about movies. Now, do we have to stop at just 2 dimensions? Of course not. By adding even more dimensions, we can create finer distinctions and better recommendations. And sometimes these distinctions can lead to an awesome business opportunity. Take something like Netflix, for example, and how they recommend movies for their engine. But it's not always the case. The danger of memorizing or overfitting always exists here too. So the idea is that we have an input n number of dimensions. What is n in the case of movies that we looked at? Well, it's 500,000 movies. Remember that the movie ID is a categorical feature. so we'd normally be one hot encoding it, and n is 500,000. So in our case, we've represented all movies in a two-dimensional space. So the dimensions, d equals 2. The key point is that d is much less than n. And the assumption is that user interest in movies can be represented by some d aspects or dimensional aspects. In all of our examples, we used 3 as the number of embeddings. You can of course use different numbers, but what number should you use before you train? This is a hyperparameter in your machine learning model. Hyperparameter means you set it before model training occurs. You have to try different numbers of embedding dimensions because there's a trade-off. Higher dimensional embeddings can more accurately represent the relationships between the input values. However, the more dimensions you have, the greater the risk of overfitting or memorizing the dataset. Also, the model gets larger and larger and tends to have slower training times. A good starting point is to go with the 4th root of the total number of possible values. For example, if you're embedding movie ID and you have 500,000 movies in your catalog, a good starting point might be the 4th root of 500,000. Now the square root of 500,000 is about 700, and the square root of 700 is about 26, so I'd probably start with something around 25. So in hyperparameter tuning, I would specify a search space between either side of that, 15 and 35. Of course, this is just a rule of thumb. Another really cool thing that you can do with features besides those embeddings is to combine your features to create a new synthetic feature. Combining features into a single feature, better known as feature crossing, enables a model to learn separate weights for each of the combinations of features. A synthetic feature is formed by crossing, or taking the Cartesian product of individual binary features obtained from categorical data or from continuous features via bucketing first. Feature crosses help represent nonlinear relationships. Now, a crossed column does not build the full table of all possible combinations. That could be very large. If you use SQL, cross-joining accidentally can blow up your whole system. Instead, it's backed by a hashed column, so you always know how large the table is. Back to our real estate example. To train the model, you simply need to write an input function that returns the features named in the feature columns. Since you're training, you also need to have your correct answers as labels. Now you can simply call the train function from the Keras API or from a custom model build, which will train the model by repeating this dataset 100 times, for example. Now you'll see how batching works later, but for those of you who already know the concept of batching, the code is written here, trains on a single batch of data at each step, and then this batch contains the entire dataset. When passing data to the built-in training loops of a model, you should either use NumPy arrays if your dataset is small and will fit into memory, or tf.data dataset objects as you learned here. Once you've defined the feature columns, you can then use a dense features layer to input them into your Keras model. This layer is simply a layer that produces a dense tensor based on your given feature columns. After your dataset is created, passing it into a Keras model for training is quite simple. As you see here, model.fit. We're not going to do that just yet though. You'll learn and practice the actual training of your model in a later video. First, you got to master dataset manipulation with the Keras API.